Welcome to the comprehensive walkthrough of LeetCode problem number 853, Car Fleet. In this video, we will explore the real-world scenario modeled by this problem, in which multiple cars travel along a straight highway towards a destination, and fleet formation depends on their arrival times. You will learn about the nuances of the problem statement, see a careful examination of all provided examples, including edge cases, and gain insight into high-quality Python and Java implementations. We'll thoroughly discuss solution strategies, step through examples, analyze algorithm complexity, and share tips for interviews and real-world situations. By the end, you'll not only know how to solve LeetCode problem number 853, but also understand the underlying principles and various approaches. Let's get started. Let's carefully review the problem statement for LeetCode problem number 853. You are given n cars traveling on a single-lane road towards a destination, defined by the target position. Each car starts at a certain position and moves at its corresponding speed. The cars cannot pass each other but may catch up, merging into a fleet that travels together at the slower car's pace. Your goal is to count the number of such fleets that reach the target. Let's go through all the examples provided by LeetCode. In example 1, with a target of 12 and 5 cars at positions 10, 8, 0, 5, 3, and speeds 2, 4, 1, 1, 3, we see that the car at 8, with speed 4, would reach the target faster than the one at 10, speed 2, but since it cannot pass, it catches up and forms a fleet with car 10. The car starting at 0 and speed 1 is quite behind, but car 3 at speed 3 will catch up with it, forming another fleet. The car at 5 with speed 1 is out of reach and forms its own fleet. The answer is 3 fleets. For example 2, only a single car is present. Naturally, the answer is 1 fleet. Now, example 3, the cars at positions 0, 2, 4, with speeds 4, 2, 1, eventually catch up before the destination, all travel together as a fleet. The answer is 1 fleet. Let's also consider the constraints, up to 10,000 cars, target between 1 and 10,000, all speeds and positions are positive and positions are always less than the target. Edge cases include all cars having identical positions and speed, which results in each car becoming its own fleet. If cars start at the same position but have different speeds, the faster car will catch up and form a fleet with slower cars ahead. Cars that have already arrived at the target are counted as fleets. Understanding these cases ensures our solution is robust. Let's continue considering more edge cases for LeetCode problem number 853. If there are no cars on the road, then, of course, the solution should return 0 fleets, as nothing arrives at the target. If cars start at different positions but arrive at the target at the same time, they are considered to form a fleet either at or just before the target. Another interesting situation occurs when all cars start at staggered points, but each moves strictly slower than the one ahead of it. In this case, no car can catch up to those ahead, each one forms a separate fleet upon arrival. Covering all of these scenarios ensures our understanding and implementation will be thorough. Let's discuss possible approaches for LeetCode problem number 853, Car Fleet. The most naive strategy is to simulate each car's trajectory, checking dynamically for catches and merges. However, this quickly becomes inefficient with large datasets. A more refined method is to sort cars by their starting positions, proceeding from those closest to the target. By calculating their arrival times and using a stack, we can efficiently track which cars will merge into fleets. This sorting and stack-based approach is not only faster but also conceptually intuitive, as it lets us process cars in order and decide fleet formation based on their arrival times. Other ideas like using 2 pointers or a priority queue exist, but the sorted stack route is the most direct and efficient, making it ideal for this problem. Now let's break down the detailed algorithm for LeetCode problem number 853. First, pair each car's position and speed to easily process together. Sort these pairs by position in descending order, so you process cars from closest to the target to furthest away. For each car, compute the time it will take them to reach the target. Iterate through the sorted cars, using a stack to track current fleet arrival times. If a car arrives later than the last fleet, push its time to the stack as a new fleet. If its arrival is earlier or equal, it merges into the previous fleet, and we do not increase the fleet count. The final fleet count is simply the number of elements, or arrival times, in the stack. This structure leverages the fact that cars cannot pass one another, relying solely on their relative speed and position to form fleets. In terms of implementation details for LeetCode problem number 853, we pair each position and speed using tuples or objects. When calculating arrival times, use float division for accuracy and avoid rounding errors. Utilize built-in sorting functionality for efficiency. The stack should be managed carefully. You can use a list structure in Python, while an explicit stack or deque might be appropriate in Java. Ensure that edge cases such as empty input lists, multiple cars arriving simultaneously, or cars already at the target are handled gracefully. The answer to the problem is simply the final length of the stack, representing distinct fleets that reach the target. Let's look at the Python implementation for LeetCode problem number 853. First, we import list for type hinting. We define the solution class and the carFleet method, which takes the target position, a list of start positions, and speeds. We pair up and sort all cars in reverse order of position, so those closer to the target come first. For each car, we calculate its arrival time as the remaining distance divided by speed. If the stack is empty or the car's arrival time is greater than the fleet on top of the stack, we append this new time, signaling a new fleet. Otherwise, the car merges with fleets ahead and doesn't increase the count. Finally, we return the number of distinct fleets by checking the stack's length. Here is the Java implementation for LeetCode problem number 853. The logic here matches the Python approach. We first construct a 2D array of cars with their positions and speeds, then sort them in descending order by position. A stack is used to record the arrival times. As in Python, if the arrival time of the current car is greater than the top of the stack, it represents a new fleet and is pushed onto the stack. The final fleet count is the stack size. Compared to Python, Java requires more explicit data typing and uses the arrays.sort method with a custom comparator for sorting. To solidify your understanding of LeetCode problem number 853, let's walk through the largest example in detail. With target 12 and cars at positions 10, 8, 0, 5, 3, and speeds 2, 4, 1, 1, 3, we first calculate how long each car will take to reach the target. The arrival times are 1, 1, 7, 3, and 12. We sort cars by position, so we process those closest to the target first. We iterate, pushing a car's arrival time onto the stack if it's greater than the fleet at the top. If a car's time is less, it merges into the fleet ahead. The stack ends up as 1, 7, 12, yielding 3 distinct fleets. Let's look at another example with target 100 cars at positions 0, 2, 4, and speeds 4, 2, 1. We calculate the arrival times 96, 49, and 25 respectively for cars starting at 4, 2, and 0, processing from closest to the target backwards. Car 4 starts a fleet. Car 2 and Car 0 both have earlier arrival times, but since they can't pass, they merge with the fleet started by Car 4. Thus, all cars form a single fleet. This highlights how relative position and speed affect fleet formation in LeetCode problem number 853. Let's analyze the time and space complexity for LeetCode problem number 853. Sorting the cars by position has a cost of O, n log n, and iterating through them is O, n. Thus, the overall time complexity is O, n log n, which is efficient even for the largest allowed input sizes. Space complexity is O, n, due to storage for the sorted car list and the stack for fleet tracking. In comparison, a naive simulation could reach O, n squared, or worse, which is impractical. Our chosen approach optimally balances efficiency and clarity while comfortably meeting all problem requirements. For interviews on LeetCode problem number 853, stress the importance of sorting the cars and the logic for fleet merging. Avoid suggesting brute force simulation for large datasets. The stack is used to elegantly track fleet formation based on arrival times. Common edge cases to mention are cars with the same starting position or speed, and fleet merges exactly at the target. This logic can extend to related problems, like car collisions or group boat logic. Always check floating point division to prevent subtle bugs, and verify that your solution's memory usage is acceptable for very large values of n. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!